Now, we stop at the frequent diagram on Tuesday, right? And I ask you to fill in the dimensions here and over. So I expect you to do it yourself, and if you haven't filled in the dimensions yet, do it at home. And we go on from here. So remember, on Tuesday we talk about what have we talked about? We have on Tuesday we will talk about support. And to determine because of course from high school physics you have learned that for support on the ground that we have reaction forces. But now we are in the university, we are in college, so we have different kinds of support will lead to different numbers of reaction forces. For example, we have four types. We have four types of supports. Usually, we have these four types. The first one is cable and roller, pin, and fixed. And to determine how many supports we need to draw or we need to mark on the frequent diagram. We determine can we move in a particular direction. If we can move in a particular direction, and this is it means we do not have forces. But for example, in this pin joint, we cannot move up and down. So we have a support force in this direction, in the vertical direction. And here, on top of the forces, and we have moments. Can we rotate? If we can rotate, we do not have a moment. But for example, in the fixed support, the pole here cannot rotate, so we have a moment here. Okay. So if I give you other types of support, you do and then you do a work to see can you move left and right, can you move horizontally, can you move vertically, and can we rotate it? Okay, so we determine this these three and types of motion and to see whether we need to add R, X, R, Y, or M. So in the example problem, this is a fixed end. So this is a fixed end. So we cannot move horizontally, and we cannot move vertically, and we cannot rotate either. So we have EX, EY, and ME. And for this cable, we have the motion. It cannot move this way, but it can move perpendicular to the direction of cable. This is okay, but this is not. So we have one force here, 115 kilonewton here, because the question has given us that tension in the cable is 115 kilonewton. So we write it down here. Is that okay? So this is the three-point diagram. Remember, in the three-point diagram, we need three things. The one is the contour, and the second one is the external forces, all external forces, and the third one is dimensions. Do we need to draw this? Do we need to draw these forces? No, because these are internal forces. Okay. These are internal forces. And because our free body ends here, so these are external forces. Okay. The forces in this cable are internal, so we do not need to draw these. Okay. Now, after we draw the three-point diagram, we go on with equilibrium equations. To And there's one thing which looks different, but it is useful, especially if you don't know what to do. First, I recommend you to write equilibrium equations. What do we mean by equilibrium here? What do we mean by equilibrium here? What equation should we write here? What does it mean by equilibrium? If we write it in equations, summation f equal to 0 and what else? Summation f equal to 0. Okay. Remember in everybody that we on top of summation f equal to 0, we have summation f equal to 0 because this probably means that we have no rotation. It's okay. Now, and so after that we can write we have three equations here because we have summation f equal to 0, summation fy equal to 0, and summation m equal to 0. And same as before. Of course, you write down the equations, and here E is plus 150 kilonewton sine theta equal to 0, and theta is this angle. And let me write down more equations first, and then I'll just have to write f ey minus 100 sine theta. And let me stop it here and take your time to write it down. Now, if you have finished writing these two, you can think about how do we write these the first one, and we can I will write down it. And also think about that do you need to write anything in front of the equations? Now, as I think I have talked about this in chapter 2 that you may have mistakes in writing this equation. So how can you write anything to help me understand what you write? Can you write anything here to help me reading your answer? Here, for example, we are talking about forces in x direction. We are talking about forces in the x direction. So what should we write here? And we are talking about equilibrium. So we can write summation and summation f x equal to 0. And please show that which side is positive, and by writing an arrow and writing a sign here. Okay. This one positive is to the right, so you can write summation f is equal to 0, and you can write you can show the direction which is positive. In this equation, in this question, that it is positive when it is to the right. So what can we write here? Oh, before the second equation. Summation fy equal to 0, and which side is positive? Up or down? Up. Okay, so we have. Now to the last equation. Now we can take the moment about any point. We can take the moment about C. We can take moment about A or B or D or E or F. And it is up to you. You can take any point. But of course, the easiest point is to take E, because the moment out of EX would be 0, and the moment out of EY is also 0. So it is easier to take point E. So now we take point E. And then for this is it's up to you how to write it. And summation M E equal to 0. And counterclockwise as positive. Counterclockwise as positive here. Now, ME plus we have the four forces. We have the 4 forces here. We have the 4 forces here. So we have 4 forces, and the moment arm can be written down. And then so it should be something like this. Go home and check it. And remember, one of them is positive, and another is negative. So for point, this is written down. And for why is it one of it is positive, another is negative. So we look at I will come back in a minute. So we look at the figure again. For point E, these 4 forces are with respect to point E, that these 4 forces are counterclockwise. While this force here, the cable tension, is clockwise. So we say this counterclockwise is positive, so this one is negative. So we say we are defining this counterclockwise as positive. So because this force is the moment created by the tension is clockwise. So this one is negative. It's okay. Now, and after you get these three equations, and this should be easy to use. And remember, when you write down the answers, then please mark the factors in with arrows here. Of course, to me, I accept this, but if you go to examination outside, that they may need you to write it in arrows. Okay. I'm okay with this, but just take note some professors would ask you to write it in this way. Now, and we go to the before. Is that anybody still writing this? No. Okay. And let's go to the last point. And I've mentioned that we take in the question about we take the rigid body as this. And how about we take the rigid body as here? We don't so we take the cable PD away from the rigid body and we only consider this part. What that it means that the tension of the cable TPD, the tension of the cable TPD will be an external force. Of course, it is because the cable is not a kind of rigid body now. And the free body diagram should be drawn like this. But what happens next is, if you assume this structure as a rigid body, this force, this TPD can be, and of course they have the same line direction. What can we do with this TPD? We can move it along the line of action to here. Okay, the force can move to here because of the principle of transmissibility, which is on page 20. I think. 21. So based on the principle of transmissibility, that these force can be moved along the line of action from here to there. So these two forces are cancelled out. Okay. So you can from the beginning you can set the free body to be here or to be the whole structure. That the result should be the same. Okay. The result should be the same. Should I? Okay. The key point is this force can be moved to there. Because we say this is a free body, and this can be moved according to according to the principle of transmissibility. According to its EG. According. According to. Okay. Now, before so if you have finished writing this page, let's go to page 42, and I'll come back to page 41 on Tuesday. Let's go to page 42. And for this equation, that it is quite for this problem, this is quite it looks a bit difficult because there are no numbers. We only have L, we have delta, beta, and we have K and so on. We do not have any numbers, that it looks quite difficult, but this is not difficult. Now, and just to go through English. Are there any words that you have not seen or you don't understand? You can spell it out and are there any words that you don't understand? I assume that there are some. I think there are some words that are not easy. Are there any words that you don't understand? Okay, and hold on. And anyway, anything else? Do you say 必须拉一条那一行，或者是那一个字，或者是你拼出来也可以。第二行 ，spread okay. Okay. Anything else? Any more? You are okay. Okay, and look at this one. Now, let's go on. And if you go to remember, if you have questions on textbook that your first on textbook and you don't understand that, it is better to ask your professor rather than to look up a dictionary. And because if you go to polar usually means this one, okay? But here in engineering, it means it should be this one. This one, okay? Now, spring, of course, if you look at dictionary, it is time of a year, but here we means and stretch is because for a spring that we have I don't have a spring here, but so for a spring then it can be made longer or shorter if you pull it. So unstretched means before being put longer. So this is because being long is stretch, so unstretch is without stretching. Okay. The right is going down. And satisfied. I think these are the words that you may find it difficult. Are there any words that you don't understand or you are not sure about the meaning? Now, if you are so what does it ask for? So we are not determining something, but we are derive an equation in theta, W, K, and L. So we are actually in other words we are finding an equation in theta, W, K, and L. So the answer should be an equation, and inside the equation we should have theta, W, K, and L. Okay. Now, so before it seems that and then when the polar is in equilibrium. Now, because this color has space W, okay? So the color has space W. The color has space W. Now, if the color has space W, it will go down and go down and down and down, right? But at the same time, this spring has a force going up. So because here that the spring force is going to the right, so it will go down, and then to some points that it will have a force going this way, and the vertical component of this spring force will cancel out this gravity W. So it will stay there. So when it stays there, it is in equilibrium. So what is the value of theta? Because it will stop at some point, right? It will stop. You go down, 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 and here it stops, and it is equal to theta. So what's the value of theta? Now, and so the question says when the color is in equilibrium, so we draw the three-point diagram of the color. We draw a three-point diagram of the color, and here we have x and y axis. And which forces should we draw here? So the first of all, we have the color has space W, so we have a force W here. And this is point B. Any other forces we need to draw? It is connected to a spring. So there is this spring force here. We say it's T. And here the angle of this spring force is given, so it is theta. What else? So there's no equilibrium, right? Then this one plus this one is always somewhere there, right? So what else should we add? Because it is because this color is along the vertical rod, so it can move here But can we move to the left or to the right? No, so what should we go here? It falls to the left or to the right. That is up to you. So let's say we go to the right. And it can move freely up or down. Move freely up or down, but can it rotate? It is something like something like this. So it cannot move. It cannot rotate freely. So we have a moment here. Remember to draw everything that you can think of here. Of course, because in the next step I will show that n is equal to 0, but draw it first. Write it down first. So we have a spring force T, and we have a force W, and then we have R. Because this cannot move left or right, so we have a force R, and then because it cannot rotate, we have a moment N here. Now this we have finished drawing the three-point diagram. Now because of equilibrium, so we have so if we have equilibrium, that means we have summation f equal to 0 and summation n equal to 0. This is not simple, but please write it down in the examination, especially if you don't know what to do. If you don't know what to do and you know it is about equilibrium, first write this down and then at least you will get 1 point, right? At least you will get 1 point. Now, for equilibrium, then we have three forces, and so we have P plus R plus W equal to 0. And but in this equation, we are not writing, because we have only three forces, we are not writing X or Y, but basically, you can of course do Fx or Fy, but I simply write it this way. And the second one, that NB equal to 0. Moment about B is equal to 0. So what do we have? M is equal to 0. M is equal to 0. You may ask that, oh, we know, so we sometimes you can see that M is equal to 0, so can we simply skip this part and not writing this. Please write everything you can think of here. And then it is okay, it is fine to show that it is equal to 0. But you need to show this in three-point diagram. Now, we have so here we have, what do we have here? We have T, we have R, and we have W. What does the question ask for? The question asks for the relationship between theta, W, A, and L, right? The question asks for this, for the equation with, let me go back to the equation. So it has to have to contain theta, W, K, and L. In this equation, what do we have? We have W, right? But we don't have the other three. So where can we get these three? Because T is related to the spring and the spring is related to K and this. And let's go on to determine T. And T and this force is Let me go back to the figure. T is the force provided by the spring. And you have learned it from your probably junior high school that for springs that what does it what do we have? We have Hooke's law. Very good. That's what does it say for a spring F? F is equal to what? K. Can I write the K delta? Delta is the change of length here. So here we have T is equal to K delta. K is the K spring constant. Okay. K is spring constant. Now T is equal to K delta, and what is delta here? And you write it down, and then I will go back to the square. I'll go back to the square at the top. I'll go back to the square at the top and to the box there, and then I will come back in a minute. So let's go back to say delta is the change of length, right? Spring elongation, or if you think this is easier to understand, it is change of length. Elongation is yeah. So it is equal to the length now plus minus and stretch. Right, that's so it is equal to what? What's the unstretched? What's the unstretched length of the spring? It says theta is equal to 0 when it is unstretched. So originally the length of spring is this point, which is L. How about now? How do we say the length now? So what's the length now? This one is L, and then this one is theta. So this one is L over cosine theta. Right. So if we have this, if we know this, then we have, I'm sorry, I think this is the right. And we have K delta. So delta, we have just just a moment ago we denoted delta. So it is equal to KL 1 over cosine theta minus 1. Now, if we have if we have this, that we consider, because R is in the x direction and W is in y direction, and this one is also in is in both x and y direction. So we can consider summation Fy equal to 0. Summation Fy equal to 0 and take order as positive. Okay, we take summation Fy equal to 0, and we have what do we have? We have E sine theta minus W equal to 0. And we know T. T is now no, so you just put in there. We have K L 1 over cosine theta minus 1 sine theta minus W equal to 0. Or simply, you rearrange the terms, we have equal to KL tangent theta minus sine theta. And this is the answer. This we simply rearrange we rearrange the terms, we rearrange the equation, that of course we can do this, and that we arrive in here, which is the answer. Now for this equation, we have theta, and just break down and in this equation, then the question asks for the relationship between theta, W, K, and L. So now we have theta, of course we have W, and we have K, and we have L. Now, so we have finished, doing the work on this problem.